So one of the goals of this first week of class is to just review some probability theory and make sure that we have a good sense of how to perform some basic probability calculations and remember some theorems. And so in this video we'll just take a look at some examples on counting. And counting can be very important when we if we want to calculate probabilities. So let's look at these two examples. So the first one really has sort of two parts to it. We'll call these A and B, and we want to find out how many different letter arrangements can be made from the letters that spell station and then the letters that spell out 11. So we'll handle each one of these separately. So for station, one maybe sort of intuitive answer might be, well, in the first spot, first we have 1, 2, 3, 4, 5, 6, 7 different spots. And we want to know how many different arrangements can we have. Well, one might think, well, in the first spot we could have any of 7 letters, right? The next spot we could have any of the 6 remaining. The next spot any of the 5 remaining, all the way down to 2 and 1. But this has something of an issue. If you think about whether order matters or not, we could try to index our different t's, right? T is repeated here. So we can write this out as station, where we have a T1 and a T2. Now, when we think about spelling, right, we could reverse the order of the T's, and that's not going to matter, right? That's always going to spell station. But in the way that we've counted so far, this way of just doing 7 factorial, we've counted these as 2 different possibilities, when really we don't want to distinguish between them. We want to count them as just one possibility. And one might think, well, we should just subtract out those 2 different possibilities, so it would be 7 factorial minus those 2 different possibilities. But that wouldn't be quite right either, because you could have lots of different combinations. So we might have this one, right, that one, and that one. Those are equivalent when we think about spelling, since we don't index the 2 different T's. So really I think what we want to do is divide by 2, because for every one of these, we have one of these. So if we divide by 2, we should get the right answer. Now what about for the word 11? Well, it's a little bit more complicated here, in that we have 3 E's, right? That's what repeats itself. So we'll number these. And we'll notice that if we did any swap of the E's, we would have the same word, 11, in this case. And we could do, E2 first, and then E1, and then E3, or E3 first, and then E1, E2, right? There are many different combinations there. And so here, since we have 1, 2, 3, 4, 5, 6, we could do our 6 factorial, but then we have to divide by the number of equivalent, equivalent spellings. So for example, this one is equivalent to E2, and then E1. Whoops, I spelt that wrong. E1. Right, those 2 are equivalent, and they're also equivalent to 4 others. And what we would do here, 6 others. So what we would do here is we would divide by 6 or 3 factorial. And really the pattern would be that if you have, say if you had 4 e's, you would divide by 4 factorial. All right, so that should give you a sense of some possible ways of counting here, and you have to think about do we have replacement or not replacement, and does order matter or not matter? So how about the second one? Well, in the second one, we're looking to form a committee of 7 consisting of 2 Republicans, 2 Democrats, and 3 independents, and we want to choose them from 5 Republicans, 6 Democrats, and 4 independents. So how many different committees are possible? Well, let's just narrow the scope for a moment, and let's think about forming a committee of 2 Republicans from 5 Republicans. Well, in that case, we would use a combination. So we have 5 Republicans, and we want to choose 2 of them. And the reason for this is that we don't have replacement, in that once we choose one of these Republicans, we can't choose them again. And here, order does not matter. So if we have, one person in the first spot and another committee with that person in the second spot, that doesn't matter, right? What matters is that that person is on the committee. So that's why we're choosing a combination. Now, in the other sort of subcommittee here is choosing 2 Democrats from 6 Democrats. So we would have 6 choose 2. And then the last one is we have 4 independents, and we want to choose 3 for our committee. And what we do here is just multiply these together, because the basic principle of counting, which you can recall from your probability prereq, tells us that multiplication is the right operation. And so here we get 600 different possible committees.